Welcome to my third lecture about improper integral. In my first two lecture, I have discussed about the improper integral of first type, the convergence of improper integral of first type, different types of improper integral, different theorems, etc. In my third lecture, I have discussed about convergence of improper integral of first kind and some problems of improper integral of first kind. In my next lecture, that is in my lecture 4 of improper integral, I will discuss about the convergence of the improper integral of second kind and the improper integral of mixed improper integral. So today I starts from this problem. This problem using Dirichlet's test or otherwise, so that the integral 1 to infinity x by 1 plus x square sin x dx is convergent. Now take let fx equal to sin x and phi x equal to x by 1 plus x square. Now to satisfy the conditions of Dirichlet's test, first of all we have to prove phi x is bounded, monotonic and monotonic decreasing, bounded, and limit x tends to infinity, phi x equal to 0. So phi dash x equal to this one, it is less than 0, and we know that if the first derivative of a function is less than 0, then this function is monotonic decreasing. So phi x is monotonic decreasing on 1 to infinity. And also mod of x by 1 plus x square, it is less equal to half for all x greater equal to 1. Therefore phi x is bounded on 1 to infinity, and this limit is 0. So all the conditions of Dirichlet's test are satisfied by the function phi x. Again, to prove integration 1 to x fx dx is bounded, we have to find out this modulus. It is less equal to 2. So this integral is bounded on 1 to x for all x greater than 1. Therefore, all the conditions of Dirichlet's test are satisfied. So 1 to infinity x phi x fx phi x dx, that is x by 1 plus x square into sin x dx, is convergent. Next, another problem. So that gamma x greater than this one, and hence deduce this result. It is a well-known function, gamma function. Beta we have already known about gamma function, beta function, etc. So we know that 0 to gamma x equal to this one, and the gamma function is convergent. We know that gamma function is convergent if x greater than 0. Now if we broken this integral into 0 to 1 and 1 to infinity, then we have gamma x equal to this one, and we know that e to the power minus t into t to the power x minus 1, it is greater than 0 for all t greater equal to 1. So its integral is also greater than 0 in that interval, that is 1 to infinity. This integral is greater than 0, and if we exclude this positive portion, then it becomes gamma x strictly greater than 0 to 1 e to the power minus t to the power x minus 1 dt. And again, since e to the power minus t is decreasing function, we know that e to the power x or e to the power t is increasing on any positive interval. So it is decreasing, e to the power minus t is decreasing, and we know that a decreasing function have largest value in the starting of the interval, and at the end of the interval it is smallest. So e to the power minus t is greater or equal to e to the power minus 1. So e to the power minus 1 is the smallest value of e to the power minus t in that interval. So e to the power minus t greater or equal to this one. If we replace e to the power minus t by e to the power minus 1, then we have gamma x greater than 0 to 1 e to the power minus 1 into t to the power x minus 1 dt, and it becomes this one. So again, to prove the second part, that is limit x tends to 0 plus gamma x equal to infinity, since limit x tends to 0 plus 0 to 1 t to the power x minus 1 dt equals to x tends to 0 plus 1 by x equal to infinity. Therefore from 1 we have this limit is infinity. Another problem. Apply Dirichlet's test to prove that the integral 1 to infinity sin x by x to the power p dx is convergent for p greater than 0. And for what values of p will the integral converges absolutely? So first of all, we have to prove that this integral is convergent if p greater than 0. And then what is the range of p for which this integral will be absolutely convergent? Because we already known that any absolutely convergent improper integral is convergent, but the converse is not true. Or so if this is convergent, so it may or may not absolutely convergent. Now if we take fx equal to this one and gx equal to 1 by x to the power p, then to use Dirichlet's test, we have to prove gx as bounded, monotonic, decreasing, and limit x tends to infinity, gx equal to 0. Since p greater than 0, so gx, that is 1 by x to the power p, is monotonic, decreasing on 1 comma infinity, and also it is bounded on that interval, and also limit x tends to infinity, gx equal to limit x tends to infinity 1 by x to the power p equal to 0 as p greater than 0. Now we have 1 to x sin x dx, modulus of that one, it is equal to less or equal to 2 for all x greater than 1. So all the conditions of Dirichlet's test are satisfied by the functions fx and phi x. So integration 1 to infinity sin x by x to the power p dx is convergent when p greater than 0. And to prove the absolutely convergent, now we have to find out this modulus sin x by x to the power p, and it is less equal to 1 by x to the power p. And we know that integration 1 to infinity dx by x to the power p is convergent if p greater than 1. So it is known by comparison, useful comparison integral. If dx by x to the power mu is convergent, if and only if mu greater than 1. So here 1 to infinity dx by x to the power p is convergent if p greater than 1. Therefore, since the larger integral is convergent, so the smaller integral is also convergent, and therefore by comparison test 1 to infinity mod of sin x by x to the power p is dx is convergent if p greater than 1. Hence 1 to infinity, since this modulus of the integral is convergent, so 1 to infinity sin x by x to the power p dx converges absolutely if p greater than 1. This is another problem. Test the convergence of 0 to infinity sin ax cos bx by x dx, a greater than 0, b greater than 0. Here x is here, so first of all we have to check whether 0 is a point of infinite discontinuity or not. First we take limit x tends to 0 plus sin ax cos bx by x, it becomes a. A is a finite quantity. Since this limiting value is finite, so 0 is not a point of infinite discontinuity of the integrand. Therefore, integration 0 to 1, this one is a proper integral and it is convergent. We know that every proper integral is convergent. Here we can take 0 to 2, 0 to 3, etc. any real number greater than 0 as upper limit. Now let us consider the integral one improper integral 1 to infinity sin x cos bx by x dx. Let fx equal to this one and phi x equal to 1 by x. Now then phi x is bounded, monotonic, decreasing on that one, and limit x tends to infinity, phi x equal to 0. And also 1 to x fx dx, modulus of this one, it becomes that one, and it is bounded. So 1 to infinity, 1 to capital X sin fx dx, that is sin x cos bx dx, is bounded for all x greater than 1. So all the conditions of Dirichlet's test are satisfied by the functions fx and phi x. Therefore, integration 1 to infinity fx phi x dx, that is sin ax cos bx by x dx, is convergent. Here also 0 to 1, this one is convergent. Here 1 to infinity, that one is convergent. So if we combine 1 and 2, we get integration 0 to infinity sin ax cos bx by x dx is convergent. There is another problem, so that 0 to infinity e to the power minus x, x to the power m minus 1 dx is convergent if and only if m greater than 0. Here 0 is not a point of infinite discontinuity of the integrand if m minus 1 greater or equal to 0. If m less than 0, then 0 is a point of infinite discontinuity, because limit x tends to 0, e to the power minus x, x to the power m minus 1 will be infinity when m less than 1. If m greater or equal to 1, then 0 is not a point of infinite discontinuity of that integrand. Here 0 to 1 fx dx, m greater or equal to 1, if m greater or equal to 1, then 0 is not a point of infinite discontinuity. And f has an infinite discontinuity at 0 when m less than 1. Now, in the convergence of at x equal to 0 when m less than 1. Here fx equal to this one, so it is greater than 0, and we take gx equal to x to the power m minus 1. Then gx is also greater than 0, and for all x that belongs to this one, limit x tends to 0 plus fx by gx equal to 1, and it is a non-zero as well as finite. So, and we know that integration 0 to 1 gx dx is convergent if it is convergent if 1 minus m less than 1. It can be taken as gx equal to 1 by x to the power 1 minus m. So by using comparison, useful comparison integral, 1 minus m less, if 1 minus m less than 1, then it is convergent. So gx is convergent if 1 minus m less than 1, that is if and only if m greater than 0. So by comparison test limit form, 1 to infinity or 0 to 1 fx dx is convergent if and only if m greater than 0. Now to check the convergence of convergence at infinity, let fx here fx greater than 0 for all x greater equal to 1, and gx equal to 1 by x square, we take gx equal to this one, and then limit x tends to infinity fx by gx equal to 0. And as the integral is convergent, therefore the integral this one is also convergent for all m. Hence the given integral is convergent if and only if m greater than 0. Now examine the convergence of the improper integral this one. Here if we put log x equal to t, then this integral becomes this one. Now we take ft equal to that one and gt equal to 1 by t. Then limit t tends to infinity, this one equal to infinity. And since 2 to infinity gt dt is divergent, so this by comparison test limit form, this integral is also divergent. This is another problem. Examine the convergence of the integral, that one. Here also 0 is a point of infinite discontinuity if a less than 1. If a greater or equal to 1, then 0 is not a point of infinite discontinuity. If a greater or equal to 1, then it is a proper integral, and if a less than 1, then 0 is the only point of infinite discontinuity of the integral. And let fx equal to this one, gx equal to x to the power a minus 1, that is 1 by x to the power 1 minus a. Then fx greater than 0, gx greater than 0 for all x belongs to this one, and limit x tends to 0 plus fx by gx equal to 1. So here we know, here we see that 0 to 1 gx dx equal to 0 to 1 dx by x to the power 1 minus a, and we know that this is convergent if and only if 1 minus a less than 1. So it is convergent if and only if 1 minus a less than 1, that is if and only if a greater than 0. So by comparison test, the given integral, that is integration 0 to infinity, and that is by comparison 0 to 1 x to the power a minus 1 by 1 plus x dx is convergent if and only if a greater than 1. Now we consider the convergence of the improper integral 1 to infinity fx dx. Here we take fx equal to this one and phi x equal to that one. Then these two limit is 1 non-zero finite number, and integration 1 to infinity phi x dx equal to this one, and we know that this is convergent if mu here 2 minus a is mu, if 2 minus a greater than 1, that is if and only if a less than 1. So by comparison test, this integral is convergent if and only if a less than 1. From 1 and 2 it follows that 0 to infinity x to the power a minus 1 by 1 plus x dx if a is convergent if 0 less a less 1. Here another problem. Last problem. Examine the convergence of the improper integral. This one. Here we take fx equal to this one and gx equal to 1 by x square plus a square. Then limit if we consider then mod of fx less equal to mod of gx and limit x tends to infinity, this one equal to 1 to pi by 2a, and therefore integration 0 to infinity gx dx is convergent, and so by comparison test this modulus integral is convergent and therefore it is convergent. Today I stop here the problems regarding improper integral of first type. In my next lecture, that is in my lecture 4, I will start from the improper convergence of the improper integral or different theorems and problems of improper integral of first type. So thanks.